the reason that they're called kilonovas is because they're about 1,000 times more energetic than a nova. And the pressure, of course, is causing the density to be higher and higher. The higher and higher density pushes the protons closer and closer together, basically a hydrogen bomb.
I would have called it super duper nova. Way more fun.
I'm finished my carbon burning. I'm going to do my magnesium burning. That helped me even less. I'm going to do my iron burning, so you get more and more frantic.
I've never seen you imitate a star before.
That was it.
That was a dying star right there.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. We're going to do cosmic queries today. Chuck.
Hey, Neil.
Did you collect the cosmic queries?
I did.
And they're not just random this time.
No, they are not.
They were solicited on the topic of stars that blow up.
Oh, and by that we mean those nasty stars that are just mean to all the other stars.
Oh, is that how that works?
Yeah.
Okay. I haven't checked the sociology of the galaxy lately. There's a friend and longtime friend and colleague of mine who works right down the hall, who is one of the world's experts on stars that blow up. Dr. Professor Curator Michael Shara. Mike.
Good afternoon.
Welcome back to StarTalk.
It's a real pleasure to be here again.
Do you guys realize he was our first hire when we rebuilt the Rose Center?
Really?
So 25 years ago, the Rose Center's been here 25 years,
right?
But we built the Department of Astrophysics to
around
prepend that.
we got Michael, and we said, and now we can build around Michael.
And you came from the Hubble Space Telescope Institute.
I did.
So you and Hubble go way back.
I was there more than 40 years ago, and I was, in fact, the first scientific hire without tenure who got tenure at the Space Telescope Institute.
So you were there
pre-launch.
That's the origin story of the Hubble Institute.
I was hired there 7.5, almost 8 years before the launch of the telescope.
Wow. That's like being on Krypton before Kal-El was launched.
So that's it on the campus of Johns Hopkins University.
Correct.
In Baltimore.
That is right.
Right.
3700 San Martin Drive.
Whoa,
Nice.
There it is. And we were delighted that you were ready for a change, and you came to join us here.
It's been 26 fabulous years. Mm-hmm. The only condition of my hire was that I not blow up like the stars I study. I'm still here, still having
Plus, he wanted
more
some
fun
opera tickets, I think. I think that was in the deal that we cut with him.
Okay, that works.
So, Mike, tell us about stars that blow up. First disentangle the fact that the word nova and supernova looks like one is just a sort of an extra version of the other, but they're two completely different things in the universe.
They are completely different things, but there's not just novas or novae and supernovas. There are micronovas. There are dwarf novas. There are recurrent novas.
Okay.
Novas, supernovas, subsupernovas, and hypernovas. And they're all...
Now you sound like you're just making shit up right now.
Yeah, I was going to say, once you get past supernova,
Well, if you find something that is more energetic and brighter,
right,
lasts longer, and even more unexpected than a supernova, you got to give it a title.
Because you're already titled super to supernova.
Because at the time you titled that was super.
was the super.
That was the ultimate. And now we know there are things that are a lot brighter and even more, in a sense, explosive than supernovas.
So had I been around at the search for that new term, I would have called it super duper nova. Way more fun.
And when some of me and my explosive star friends are sitting around over a beer, that's what we refer to
Super
them as.
duper nova.
Super duper nova.
So let's back up. So the stars, nova, literally from Latin means new.
Right.
Yet it's the star at the end of its life, or at end of it's long lived a life before it goes nova. So it's really misnamed.
Long before it goes supernova, there's a real difference because novas.
Let's start with novas.
Let's do, in a sense, the simpler thing. Novas are stars that explode but don't die.
Gotcha.
Every nova explodes not just once or twice, but thousands of times.
Oh, it's a Christian Bale star.
These are things that explode over and over again. And there can be years between the explosions of novas. These are called recurrent novas, or centuries,
Right.
millennia, even 1,000,000 years, because something has to be rebuilt. The explosive part has to be rebuilt, and then it explodes again.
Because the star's still there.
The star, the underlying star, and it turns out that every nova is a binary star. So the stars, plural,
Gotcha.
are still there after the explosion.
Did you say every nova is a binary system?
That's
or is it-
correct.
So does that mean that one star is feeding another star?
That's exactly right. And feeding may not be exactly the right word. You might think of it as a kind of cannibalism.
Ooh.
Involuntary feeding
Oh my.
of one star by the other.
Wait.
And it's worse.
Wait, but the
It's worse
big
than that.
bulbous star that's handing over the matter,
Right.
it was asking for it because it's
It's actually in its space.
In its space.
It's in its space.
Up
It's up in its face.
Up in the space.
And the little star is like, why are you on my grill, man?
that's exactly correct.
I'll give you that. It's also worth remembering that there's a kind of zombification going on here because the little star is almost always what we call a compact degenerate object, either a white dwarf or a neutron star or a black hole.
Hi-ho. Listen, I got a gambling problem. What can I say?
So it's not just you have some overbearing, bulbous, hasn't been able to control itself star involved, but it's actually being eaten by this nearby very compact, very
So in a
dense.
nova,
Degenerate.
it actually takes two to tango.
Very much so.
Right. Okay. Tell me exactly what's happening. So the secondary star, is that what it's called? The big one.
It's sometimes called the donor, sometimes called the secondary star.
That star also has to be in a late stage of its own life to become a red giant and swell to become so large to overspill the gravity boundary.
That happens in some cases, but it doesn't actually have to be a red giant. It can be a main sequence star, still burning hydrogen.
Just like the sun.
Just like the sun.
Our sun, yeah.
Identical to the sun in every way. And the reason that it's starting to be accreted onto, or it's feeding the companion, is just that it's so close
Right.
that as a little bit of it expands, just a tiny bit of expansion during its evolution, the nearby star has enough gravity to be able to immediately vacuum off, suck off any material that expands beyond a certain radius. So it doesn't have to be
close
a red
orbiting
giant.
ones. It doesn't have to. Okay, gotcha.
Wow. So have we ever taken a look at these systems and seen like planetary systems around them?
We've looked. It would be an extremely unpleasant environment for any planetary system. Nobody has found one.
Okay.
Even if it was there, it would be extremely hard to find because there's a lot of light being given off by these guys. They're intrinsically,
Gotcha.
they have hot spots.
I see.
The accretion disk, the donut of material around the compact star, is quite bright. It flickers like crazy. And any planet would be, of course, thousands of times or hundreds of times less massive than the two stars.
Well, just when you say the disk flickers, is that every time a little bit of matter hits it, you get a little bit of bright spot?
You have stuff being sucked off the donor into a donut-shaped accretion disk, as it's called, around the compact object. And as that stream of material bangs into the donut,
You got hot
it
spots.
causes flickering continuously on a time scale from minutes to seconds, probably down to milliseconds.
And the donut is a mechanism to feed the compact object.
That's
Okay, so now, why doesn't it just explode as soon as stuff hits the surface?
you need to not just get a little bit of hydrogen onto the surface, because if you put a bit of hydrogen on the surface of a white dwarf, it can just sit there. The hydrogen doesn't feel the need to explode until it reaches a certain density and temperature. And that critical density and temperature mean that in the case of let's talk about a white dwarf star, just for concreteness. That's what most novas are, white dwarf stars. These are guys that are about the mass of the sun, so several 100,000 times the mass of the Earth, but they're only the size of the Earth. And how much hydrogen do they need to accrete in order to become explosive? Well, because they're the size of the Earth, about 8,000 miles across, they need to accrete about a mile of hydrogen, so about a Pacific Ocean's worth of hydrogen onto their surface. At that point, the density and pressure at the bottom of the Pacific Ocean of hydrogen is about 10,000 grams per cc, so about 1,000 times denser than lead. Temperature reaches 40, 50 million degrees. At that point, the hydrogen becomes highly explosive.
Nice.
Boom. You blow up, and you get to be about 100,000 to 1,000,000 times as bright as the sun for a few
I need
weeks.
to clarify something.
Yep.
Hydrogen as a gas
Right.
is explosive. So that's not what you meant.
Right.
Okay. So be precise there.
It is not the kind of explosion that you're thinking of in the Earth's atmosphere where hydrogen combines chemically with oxygen.
Right.
All the humanity.
From the Hindenburg. Yes. Yes. The last
Sorry for going dark there, guys. Sorry.
That's it.
the last dirigible ever filled with hydrogen.
Right.
Yes. Yeah.
We're talking something 100,000 or 1,000,000 times more energetic because we're talking nuclear reactions.
Right.
So instead of the hydrogen combining with oxygen, we're talking about protons smashing into each other, overcoming the charge
Repulsion.
barrier between them,
Right.
fusing together,
Nice.
basically a hydrogen bomb.
Yeah.
And once you do that, once you become 1,000,000 times as bright as the sun, we can see you not throughout the Milky Way, not just throughout the Milky Way, not just in the Andromeda galaxy, but I've tracked more than 100 novas in the Virgo cluster of galaxies, 50 million light years away.
Wow.
So these become really, really
Super
bright
bright.
objects.
Yeah. So I love the idea that I've never heard it put before when you say the Pacific Ocean amount of hydrogen, because it's also pressure, right, that you need, right?
That's exactly right.
Yeah, so it's like the same way as you get to the bottom of the Pacific, you would be crushed because of the pressure. It's that same pressure that is causing this ignition.
And the pressure, of course, is causing the density to be higher and
Right.
higher. The higher and higher density pushes the protons closer and closer together.
Which ordinarily
and lets
don't want to
fusion
get
go
together
underway.
Right.
because they have the same charge.
Science is amazing. I'm sorry. It's just so damn cool. It's just so cool, man.
Let's put a pin in that. And now let's go to supernova,
Yep.
and then we'll go to our Q&A.
It used to be thought that there were two kinds of supernovas.
Let me guess, type 1 and type 2.
That's precisely right.
Two types.
And of course, it turns out that the type 1 supernovas are in what we call population 2
Yeah.
galaxies, and the type 2 supernovas, just the opposite.
One of my early books, there was a chapter titled The Confused Person's Guide to Astronomical Jargon.
Nice.
That was the name of the chapter. That should be like required
Right.
reading, I think. for
Yeah,
everybody.
exactly.
Yeah.
So now with almost a century's worth of study of these things, we know that in very first principles, the broadest way of looking at these supernovas are that they're either what we call core collapse supernovae.
Okay.
That is massive stars where the inner part of the star, which holds itself out against the gravity of the rest of the star, loses that pressure. Somehow that inner part of the star collapses in on itself.
Okay.
And when it does so, the whole star implodes, bounces on the inner part of the star, and then much of the star is blown away. So that's a core collapse supernova. And the other kinds are what are called single or double degenerate supernovae. And these are stars that are mostly white dwarfs,
Okay.
that have also lost their source of pressure in their centers, collapse down to become probably neutron stars in most cases, releasing enough energy to blow off the outer envelope. And these two very different kinds of supernovas have very different properties in terms of what we see in their spectra, what we see in the ejecta, the stuff that gets blown off of the two stars. So we know that they're two very different things. And within the core collapse supernovae, they can be anywhere from 20, 30, 40, up to 100 times the mass of the sun.
Okay.
While the other ones, the degenerate supernovas, are somewhere between about 1.4 and about 3 times the mass of the sun. So much lower masses.
And those are the ones that also don't pay child support.
Never.
Yeah.
But they are the ones that let us discover the dark energy.
Nice. So as I'm hearing you describe this, I can't help but recall to mind like neutron stars, because that's basically what you described, if I'm right, neutron star. And then if it's spinning very fast, it's then a pulsar, right?
If it's spinning very fast and has a magnetic field,
Oh, okay.
that's an extremely important part of it, which it
Okay.
almost certainly does.
And the magnetic field can't be aligned with the axis of
Not
rotation.
perfectly. It's got to be
Right.
tipped.
Okay.
You get all of those things, you're going to end up with a pulsar for a while.
For a while.
Maybe 100 million years. Well, listen, that's just a blink.
That's a blink in
to
the
an
eye?
astronomer.
Wow, look at that.
After some time, after that 100 million years or so, it's going to go radio quiet. It's not going to be as interesting. So for every pulsar we see wandering around out there, there are probably 100 quiet, or listen to,
Right.
that we can hear the beep, beep, beep. There's probably 100 quiet ones.
So now here's my last question, because I know I don't want
That's not your last question.
I know it never is, but I don't want to take up time from the people.
Well, are you about to ask a question?
Yes.
Well, where's your Patreon?
Oh, come on now. I'm asking on behalf of, let's see.
Hey, StarTalk fans. I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcast and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk.
Everything you just said
Yep.
seems to me like the same things in the process of creating a black hole, except you need a lot more mass. And then what happens in the end is that we can't see into it because at some point the gravity is so great that light can't escape. If that is the case, and this process is the same, just bear with me.
Yep.
Why can't we study this to kind of know what's happening inside of a black hole?
the answer is a few-parted.
Okay.
So first of all, we only know for sure of one kind of all the core collapse supernovas, because there are different kinds of flavors.
Oh.
Okay, so think of them as ice cream. There's chocolate, vanilla, strawberry, raspberry,
Terry Garcia.
so there's many different subtypes of the massive star supernovas. We know of the ones that are called the type 2 plateau supernovae, that they have red supergiant progenitors.
Okay.
That is the stars that make these kinds of supernovas,
Right.
and almost certainly end up as black holes, as modest mass black holes are red supergiants. But
But do you
there's
get a supernova with the black hole or not? Or does everything just get sucked in?
some of the stuff gets blown off.
Okay.
We think, yet, and the reason we think that is we've seen lots of supernovas and we look at them. We've observed lots of supernovas, and when you look really carefully, a century later, 2 centuries, 1,000 years later, we see a supernova remnant. We see a big expanding cloud of gas. The Crab Nebula is maybe the classic example.
Can you also measure the rate at which the gas is moving away?
We
And
can.
then turn the clock back and say it must have started.
1054, for sure. Absolutely.
Very
So
cool.
that's how we know with beyond the shadow of a doubt. And we know that there is a very bright, rapidly spinning neutron star in the center of that supernova. There is a beautiful pulsar there too. So there we have absolute proof, as much as you can prove anything ever in astrophysics, that you had an intermediate mass star, maybe 10 or 15 or 20 solar masses, that collapse down to give you a spinning neutron star and the supernova remnant. But there may be dark supernovas too. There's a good case to be made for some stars, very, very bright luminous stars that just go and disappear out of the universe.
I've seen a video of that. It's pretty, I mean,
cool.
an animation of it.
Yeah.
It's scary, actually. It's like the whole thing gets flushed down its own toilet. And there's
Nice.
nothing,
Like a snake eating itself.
Yeah.
If you will, except that it's not gone.
Right.
The black hole is still there.
Right.
And if you are a highly adventurous astronaut racing through the universe and you don't have the right sensors, you're going to go right down the throat of that snake that swallowed itself, and you're not even going to know it. It's just going to take you right down.
Which of these is responsible primarily for the heavy elements in the universe?
Probably a combination of them.
Combination, okay.
So one kind of nova that we didn't mention before are kilonovas. And the reason that they're called kilonovas is because they're about 1,000 times more energetic than a nova, which is about 1,000,000 times the brightness of the sun. So these are about 1,000,000,000 times the brightness of the sun. And a supernova, which is about 1,000 times brighter than a kilonova. So you could call it a meganova, except we call it a supernova. And then there are things that are 10 to 100 times brighter than that, and those are the hypernovas. And there's different mechanisms, different things that are going on in each case.
So, but you have that inventory, so we can account for the elements in the universe.
Yes, and we have a fair idea just by taking spectra, breaking up the light into all its components and measuring what's coming off in supernova remnants, how much iron, how much silicon, how much nickel is being produced in different kinds of supernovas. So certainly some of the core collapse supernovas are producing certain kinds of elements. Probably the collapse of the degenerate objects is producing much of the iron in the universe. And ordinary novas are probably producing a good fraction of the nitrogen in the universe. So every time you take a breath, you're breathing in some of the excreta. Every breath you take is some of the excreta of a nova.
Well, when you say it like that, it's not so pleasant. I was about to say, thanks, Supernova, but now I'm like,
So what you got here?
All right, here we go. Let's jump into it. This is from Dipin. Hello, Dr. Tyson, Dr. Shara, your lordship. First, we're taught that matter in neutron stars is strange. Then we say that collision of neutron stars creates heavy metals like gold and platinum. How are these normal metals created from strange matter?
Great question. The answer is that while the matter inside a neutron star is at not just strange, but insane sorts of densities, one with 13 or 14 zeros after it, grams per cubic centimeter. So quadrillions, trillions or quadrillions of grams per cubic centimeter. Once the kilonova has exploded, maybe some of it fallen into a black hole, but some of it's been blown off, that expanding matter starts going down in density. And so the free neutrons inside the neutron star start combining with each other. Some of them start decaying into protons. Neutrons and protons combine to make nuclei. And that's how you get ordinary matter, because you get out of the incredibly dense state inside the neutron star. You've escaped. You're free to become yourself. You're free to become gold or platinum.
That's right, Dad. Oh, that's very cool, man. Great question. All right, this is Stacy Hughes. Hello, all. This is Stacy Hughes from Nebraska. I have heard somewhere that large stars are going to stop being born before other stars. If that is true, how much sooner than the last stars dying out will the last supernova be? And what types of stars will be born after the last supernova? And will we still be here when that happens? Let me take that last part for you.
Doesn't look like it.
So go ahead.
Given the rate at which humans have been developing technologies capable of destroying all of us, I'm not sure. I'd say we have maybe a 50-50 chance.
Okay.
Okay, but if we make it through the next century or two, maybe we'll get smart enough, or maybe we'll disperse away from the Earth and be able to hang in there. Let me answer your question about the most massive stars. When we look out in the Milky Way galaxy, we see large clouds of gas and dust, including things we call giant molecular clouds. And these are the objects that give birth to new stars. And we see the same kinds of objects in nearby galaxies, and we can image them in great detail with the Hubble Space Telescope or the James Webb Space Telescope. And we see clusters of thousands of stars being born now throughout the Milky Way, throughout nearby galaxies. And there are almost always some really, really luminous, very, very massive stars in these youngest clusters, up to about 100 times the mass of the sun.
Okay.
Will this eventually stop? Well, we see galaxies where this has stopped, because when galaxies crash into each other and merge, most of the gas, the hydrogen gas, the stuff out of which stars is born, much of it is liberated.
Right.
It's blown out of those galaxies.
Okay.
We're left behind with an elliptical galaxy that doesn't make many stars anymore. And so at some point, it's possible, in fact likely, that every galaxy in the universe that has hydrogen in it will have lost all or most of that hydrogen. And when that happens, star formation is going to ramp down and eventually stop, billions of years into the future. But not right now. Will we be around billions of years in the future? No idea.
Yeah, come on.
Cannot tell you.
Yeah, I can tell you. I can tell you right now.
You got the answer now.
I got the answer right now,
Okay.
Stacy. That's a great question, though. And these gas clouds that you see, are these the same as stellar nurseries? Is that what we...
No.
That's exactly right.
Oh, okay.
The nearest prominent one, you can see it with the naked eye, is the Orion Nebula.
Right.
Underneath the three stars in the belt, there's this lovely glowing cloud.
And if you're in the southern hemisphere, they're above the belt.
That is true. And there's one...
So like us to hit below the belt.
And there's one O star, one of those massive stars that's doing all the ionization, all the excitation. It is the guy that is responsible mostly for the central part of the Orion Nebula looking like it is. If it weren't there, it'd be a much less interesting thing to look at.
Wow. That is super cool, man. All right. This is Christopher Peffers. And Christopher says, hello, Dr. Shara, Dr. Tyson, Lord Nice, Chris Peffers here from Charleston, Indiana. Dr. Shara, you've spent decades studying exploding stars and binary systems, some of the most extreme objects in the universe. For people who might think space is just empty and still, can you walk us through what happens in a closed binary system where one of the stars steals matter from another, eventually causing a supernova or a nova or even a supernova? What does that cosmic drama look like? And should everyday people even care about these distant events? Do they help us understand our own sun, or even where the elements that make up life on Earth come from? Thank you for your work, sir. There it is.
Well, first of all, it's my pleasure. I appreciate the pat on the back, sort of the verbal pat on the back.
Right.
I do it. The reason I've spent decades doing this is because I love it. Astronomy, in some sense, is my hobby. The fact that someone's willing to pay me to do it and to teach
That's
the
the old
public
adage.
about it.
Take your hobby, make it a career, and you'll never... Was it
Right. Well, yeah. So you'll never be something.
You'll never work a day.
You'll
in your
never
life.
work a day in your life. That's it.
And it's been a joy. And in some sense, I haven't worked a day in my life because it's always been fun. It's always been great.
That's
and
pretty cool.
I get to work with lots of bright young people doing their masters and PhDs and work with them all the time. So it's a glorious way to spend one's life. Okay, let's zoom in on one of these systems, one of these binary systems. And I'm going to pick a particular system that you're going to be able to see with your naked eye next year or the year after.
Okay.
Okay?
All right. Relatively short period of time.
I bet he's talking about T Coronae Borealis.
And Neil is just thrown a
There it is.
bullseye.
Don't tell anybody. But I think
Exactly
stay
right.
quiet. And when he says it, just
Then
act,
we'll say,
act,
I will act surprised.
act surprised.
Okay.
Yeah. So
What is it?
So there is a star called T Coronae Borealis.
Oh, okay.
Woo, surprise. That is going to get brighter than the North Star, brighter than Polaris.
Wow.
Either tonight or tomorrow night or sometime in the next year or two.
Okay, I have to jump in here.
Okay.
So I don't want to cast shade on how bright it's going to get, but Polaris ain't that bright.
Okay.
Our North Star,
Which I've heard you say this.
even
and
9 out of 10 people, you say, what's the brightest star? They'll say
say
North
the
Star.
North Star.
It is not in the top 10. It's not in the top 20.
Right.
It's not in the top 30.
Yes.
It's not even in the top 40.
Yes.
Okay? So I just put that out there right now. And what the core bore, what is that reference?
Coronae Borealis, Latin for a northern crown. And it is a constellation, a little grouping of stars that looks like a semicircle, a crown.
Yeah.
Okay.
Gotcha.
Actually, a tiara would be that, right?
That's a better term.
It would be, wouldn't it?
Yes, exactly.
Much better name.
So is there a crown in the southern hemisphere
There
too?
is Coronae Australis.
Okay, good. So that's why you specify the Borealis.
That is correct.
Yeah, okay. So pick it up from there.
We saw this star last erupt about 79 years ago. And then 80 years before that, we saw it erupt as a nova. And each time it became about second magnitude. And one of my colleagues, Brad Schaefer, has made a pretty good case for it having erupted 80 years before that. And then he even points out some possible evidence for an eruption in the 1200s. Cool. So this is a star. This is a recurrent nova.
Wait, nobody was looking up in the 1200s.
They were just trying to not
Not starve
get
to
eaten by
death
dragons or not starve to death.
or die of the bubonic plague. No, there were people who actually did notice changing stars, things that were wild. And of course, there were no electric lights in those days.
You had a
It
lot
was
more
all-
stars to look at.
There were
Actually,
Sorry, it was the 14th century, which was the only century where the population of the world was lower at the end than it was at the beginning. From the bubonic plague and all of this.
yeah.
Black Death will do it every time.
That's why I can't stand it. They called it the Black Death. Yes. Of course, the most deadly of deaths has to be the Black Death. No, go ahead.
Okay.
I'm being silly. Go ahead.
No worries. So this star, this massive white dwarf, is cannibalizing its companion, which is in this case, a red giant star.
Authentic red giant.
This is an authentic red giant.
Can you see both stars when you look at them? Or are they too far away?
You can see neither. It is roughly 13th magnitude in quiescence. So if you look with a terrific pair of binoculars, you still can't see it. You need at least, if you want to see it with your naked eye or with your eye, you need at least, say, an 8 or a 10-inch telescope to be able to see
a
it
really
at all.
good backyard telescope,
backyard telescope.
Would catch this.
We'll see it when it's in quiescence,
Okay.
and it's going to jump in brightness approximately 100,000-fold to reach roughly the brightness, a little bit brighter probably than Polaris for a few hours, and then it'll fade away, and then on a time scale of a week or two, you won't see it again. And you won't see it again for another 80 years.
So when I was in the Pacific Northwest, I took a photo of your star. And I don't know if I got to show it to you. Did I? Did I ever show it to you?
I think you might
Because,
have
there was a chance it could have blown up while I was looking at it.
Exactly.
And then I'd be the first.
to have seen
Right.
it, or at least have recorded
I'd have been
it.
the first out of the box on that one.
Yep. Everyone wants to be the one to see it starting on its rise.
Of course.
And so people have little charts, and okay, there's T Coronae Borealis.
So somebody's watching this thing every night.
Of course.
Someone is watching it basically every
24 hours a
minute,
day.
24/7.
Because half the world is dark at any given time. And we got people everywhere.
Of course you do.
There are tens of thousands of so-called amateur astronomers who are every bit as professional as professional astronomers.
In that community,
Go ahead.
it is a badge of honor to say, I am an amateur astronomer. If you say that, you can ask them any question about the night sky and they'll have an answer.
They know.
Even some of my colleagues wouldn't know because they know the night sky. They're out there every night, as I was when I was, had my backyard telescope, except my rooftop. There's no backyard in the Bronx. I was hauled to the roof.
So the thing for me that is most exciting about T Coronae Borealis is that as a recurrent nova, it was predicted, and there were only 10 recurrent novae known in the whole Milky Way about a decade ago. It was predicted that, boom, you blow off a shell of matter, then 80 years later, boom, you blow off another shell, another. The stuff doesn't all come off at the same speed. Some of it comes off at high speed, some at a lower speed. So what that means is when the next shell goes off,
someone's going to overcome. The fast stuff is going to overtake the slow stuff.
Bingo. So you're going to have shells colliding with each other.
When shells collide.
Colliding, Jerry. No, that's amazing.
And so it's going to be a traffic pileup.
Right.
Whoa.
It's like, one car running into another. And if that's right, that hasn't just been happening for 80 or 160 or 240 or 320 years. It's been going on for thousands or tens of thousands of years, which means you've got hundreds or thousands of shells piled up on top of each other. That means you should have a super shell,
right?
A super remnant surrounding T Coronae Borealis.
Where the fastest stuff is plowed onto itself.
Right.
Bulldozed its way through.
But that's not all. Wait, there's more, because as that shell builds up in mass, it's also acting like a snowplow, plowing up all the stuff in the interstellar medium in front of it.
The stuff that's there anyway as bystanders.
Is going to get mowed over and is going to be incorporated into that super shell. So there should be a super duper shell around it, and we've just found it.
Oh, he buried the lead.
What?
You heard it here.
What?
So we've been using a gorgeous new, not expensive telescope.
Oh.
The kind of telescope that so-called amateurs use, refracting telescopes. 6 of them bolted together in parallel, and we stared at T Coronae Borealis for about 100 hours.
They're not in darkness for 100 hours. I just want to make that clear.
Oh, okay.
Right. Yeah. They get the dark stuff tonight.
Right.
They close the hatch.
And then tomorrow night,
pick it up again.
we're back at it.
Okay, back at it. Okay,
Right.
go.
And so we actually have thousands of images taken over more than 100 nights of T Coronae Borealis, and we add up all those images, and we took pictures through filters that only transmit the light from hydrogen, only transmit the light that comes from nitrogen ions, sulfur ions, and so on. And we found a super shell surrounding T Coronae Borealis that's about 3 times the diameter of the full moon.
That's fabulous.
So it is 1.5 degrees on the sky. And you might then think, well, when T Coronae Borealis goes off, it's going to be like a flash bulb going off in a room full of little mirrors.
Right.
It's going to be like Christmas lights going off as this flash of light propagates outwards.
Echoes off the material.
The super shell.
One would hope that would be true.
That's amazing.
It's probably not.
Oh, no.
So the downer is we published in a paper that just came out a couple of months ago saying there's not going to be fluorescence.
Okay.
So the atoms themselves are not going to light up because they're too far apart and there aren't enough of them. It's not going to be bright enough to detect. Now, maybe, just maybe, if there was dust, little grains of silicon and carbon and other what we call refractory elements, high temperature stuff, little grains that were tossed out in the last nova eruption, the 180 years ago, those might reflect enough light for us to see as a light echo. And you know that a day or 2 or 3 after this goes off, the Hubble Space Telescope is going to get pointed at the James Webb Space Telescope.
We're very good about that. Yeah. Something happens, everybody
comes together.
We are the most come together.
Information.
We are the most come together.
We're always about a collabo.
Always, especially since not every telescope will observe it in the same way.
Yeah.
So you get different kinds of data coming together.
I always say the only people to collaborate more than rappers are astrophysicists.
Okay. So Mike, on my iPhone, I controlled a digital telescope when I was in the Pacific Northwest. Didn't even leave the comforts of the living room when I did this. See, he's old school. He's like, what? You didn't like ascend the mountain.
You did not suffer for that image?
I've been up in the prime focus cage of telescopes for nights at a time.
Tell me about it on your rocking chair.
Exactly,
Right.
exactly.
So this image, I found it, but it was behind a very modeled tree. And so the digital telescope tracks it. But so the tree ends up blurred as it's tracking the actual object. So it's a very undistinguished dot on my picture.
Had you caught it near its maximum, you would basically have saturated the image.
Yeah.
All of the image would be just one bright point of light.
Wow.
But there's no saturation anymore because this knows what it's doing. It takes 10-second images.
Yes.
And then stacks them.
Right.
Yeah, in the old days,
Right.
you
Right.
expose
You
it.
overexpose.
It would get
because you're actually-
overexposed. Right.
Now you don't have that
No,
problem
we got
because
this.
you're getting all separate images.
It's separate, and then you stack them and add them, and you get it.
Yeah.
Keep going.
All right,
What
let's
else you
keep
got?
going, man. This is really cool stuff. This is Joel Bradley, and Joel says, "Greeting, Dr. Tyson, Dr. Shara, Lord Nice. Joel here from Geelong, Australia, and I have a question regarding our favorite pre-supernova star, Betelgeuse. Whilst I understand that life of a star is extremely long from our perspective, how is the time frame for Betelgeuse going to supernova between now and 100,000 years? Is there any sign that will warn us of it happening in our lifetime, or will we just look up one night and go, oh, wow, look at that?
There it was. There it is.
was.
What's the life expectancy of Betelgeuse from birth to death?
Something like the star itself,
Yes.
if you consider the main sequence lifetime, probably a few million years.
Got it. Okay.
Okay, so it was hydrogen burning for a good fraction of its lifetime, maybe 1 million years, maybe 3 million
Again,
years.
when it's astrophysicist speaking, he means hydrogen fusion. Right.
Of course.
Okay.
So Betelgeuse was initially as a very massive star fusing hydrogen into helium. Then it left the main sequence, ascended the red, and then the red supergiant branches.
Ran out of hydrogen in its
Ran
core.
out of hydrogen, needed to do something else, needed a new source of energy. Otherwise, it was going to collapse. The core got dense enough and hot enough for helium to start fusing into carbon.
And helium has 2 protons in its nucleus.
Oh.
Now you got to get two protons
protons.
next to 2 protons. You got to be hotter than whatever you were for
Wow,
hydrogen.
look at that.
Typically, you've got to be in the 100 million degree range instead of the 20 million degree range in order for that to happen.
Okay.
So it is really hot down there in the core of Betelgeuse. Betelgeuse has only got, probably in the best case, 100,000 years to go, but it might be tomorrow.
Okay, that's a really bad prediction.
Listen,
Can you do better than that,
50
Michael?
years ago, the prediction would have been, we don't know why it's a red supergiant. So we have gotten a lot better.
Okay.
Yes, we would
Okay.
love to do better. And the answer is,
We should appreciate how far we've come.
if you give
even
me,
in our ignorance.
if you give me enough money, I will build a detector that will tell you several days in advance when it's going to go off.
Nice.
And what is that detector going to be? Well, it's going to be the biggest, baddest neutrino detector that's ever been built on Earth. Right now, we've been super clever, we, meaning physicists collectively, not me, have built enormous detectors using cubic miles of seawater or ice. The ice cube detector, for example.
In Antarctica.
In Antarctica. And a gorgeous detector right near Sicily, a huge underwater detector.
And the rapper Ice Cube goes down there and performs for the scientists. Not. Okay.
Not. But if we could build a detector that was, say, 1,000 times the volume, so instead of a mile by a mile by a mile, we'd love to build something that was 10 miles by 10 miles by a few miles at least, we'd have 1,000 times the sensitivity. Now, why do I care about neutrinos? Well, as the star is right near the end of its lifetime and just about to flash off, it's not just going to
Do
burn.
you see the light?
Do you see the light? Yeah. It's going to burn the carbon into magnesium, the magnesium into heavier elements, all the way up to iron. And you're going to get a great flux of neutrinos coming out of the core of the star in the last few hours, maybe days
Wow.
of the
Okay.
life of the star, certainly in the last couple of minutes. And then during the implosion, you're going to get another blast of neutrinos. So these will come out of the star before anything else.
Okay.
But they're not going the speed of light.
They're not.
So why? So
Doesn't matter. And the reason it doesn't matter is that Betelgeuse isn't that far away. We're talking hundreds of light years. We're not talking millions or billions of light years away. And as a result, the difference between the speed of the neutrinos,
which is very fast,
which is very
admittedly.
99.9, many nines, percent the speed of light. The difference in speed between the neutrinos and the gravitational radiation that will be
and that's going the
emitted,
speed of light.
That is moving exactly at the speed of light.
And we have something that could detect that if it happens.
We have several detectors, at least 3 up and operating now that are going to detect those gravitational waves.
Are they all collectively LIGO, or is it just the American ones called LIGO?
They're collectively called LIGO, and each one of them has its own name. For example, the Italian one is referred to as Virgo, but the LIGO, if you will, the LIGO assembly is the 3 telescopes.
We get the gravitational waves, and they will come at the same speed as the explosive light, I presume.
They're going to precede the light.
Oh, because you have the collapse.
You have the collapse, and then you got to expand again to get big enough to have a photosphere, a radiating surface big enough. So it's going to be tens of minutes to tens of hours before you see it in the optical.
This is going to be amazing.
So
when you'll see them one right after another, each of these, the sequence of events.
So we're going to see the gravitational radiation and the neutrinos arriving almost simultaneously. We may get lucky and see a few of the early neutrinos coming a few seconds or minutes early. That would be just in the last gasps of, I'm finished my carbon burning. I'm going to do my magnesium burning. That didn't help me. I'm going to do my silicon burn. That helped me even less. I'm going to do my iron burning. So you get more and more frantic.
I've never seen you imitate a star before. That was pretty good.
That was it.
Good.
That was very good.
That was a dying star right there.
And so,
because what he's doing is the star is trying to not die,
right?
And so it's finding
finding everything it can do to burn.
And if there's not enough, it's going to collapse on down.
And so maybe in that last minute, we'll start seeing a neutrino here, another one, and then tens of thousands of them arriving. And that's going to be the harbinger. That's going to tell us supernova coming.
Time.
Supernova's coming from there, that direction. If we have all 3 detectors,
you can triangulate back on it.
We can triangulate to about plus or minus a degree.
Okay.
You know, a little bit more than the area of the full moon on the sky.
Yeah, but how many supernova progenitors are in the area of a full moon on the sky?
We typically get, in a square degree, we've got millions and millions of stars. You don't know which one it is, but if you triangulate back to that 1 square degree where Betelgeuse is,
if Betelgeuse in the middle of the thing, that's
you
smoking
pretty much
gun.
know the deal.
whoop, 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 turn on your alarms.
So how bright will Betelgeuse get? Because it's already bright. It's like, what is it? It's 0th magnitude. What is it?
Maybe minus
1, maybe.
Something like that.
Yeah.
It's certainly one of the 15, 20 brightest stars in the sky.
Way brighter than the North Star.
Once again.
Right. So right now, currently, it's maybe a million times, the luminosity of the sun.
Okay.
But it's going to go to at least 10 billion times. It's going to get at least 10,000 times brighter.
Wow.
Which
so
means
that's 15 magnitudes. It'll be visible in the daytime.
It's certainly going to be a daytime thing.
It's going to compete with the full moon for brightness.
That's great.
Probably cast your shadow. My gosh.
No question.
Joel, there you have it, my friend. If you have a neutrino detector, you will know exactly when this is going down.
You'll know first.
If you get the neutrinos and you get the gravitational waves at the same time, just know, Elizabeth, I'm coming to join you, honey. Betelgeuse is about to kick the bucket, and you can watch it. So that's super cool.
One good piece of news. I mean, you're headed in absolutely the right direction. I don't want you scaring anyone, though.
Okay.
You don't need to go down to your basement or your sub-basement. Because even though there are going to be lots of high-energy neutrinos coming and whacking you, none of them's going to hurt you.
Right.
There aren't going to be enough gamma rays to fry our ozone layer.
Or make you the Hulk.
Or make you the Hulk. Or give you a sunburn. So don't worry about that kind of stuff. It's just going to be something ultra cool that you can walk out and see something that really nobody has seen since the 1600s. We had 2 supernovas almost
Kepler
back to
had
back.
one. Was that, how bright was Kepler's supernova?
It was also the same kind of brightness, maybe not quite as bright as that.
In the daytime?
It was seen in the daytime probably for a month or two, but I got to go check that.
So let me ask you both of this then. The most famous star in the night sky and also reportedly shown during the day, the Star of Bethlehem. Do we have any real record of what that was?
Go on, ask the Jewish man about the Star of Bethlehem. Go ahead.
So my forefathers did not draw a diagram or a map of where it was. In fact, this only appears in the New Testament.
Right.
Yeah.
As a star in the east.
Star in the east.
You know, that's a little
too
vague.
vague, huh?
You think?
Little too vague, huh?
A little bit.
Yeah, gotcha.
And so what can we do that is maybe better? Well, we can go back to the people.
That's all. That's the best info
so
available.
That's it.
Well, we can try and cross-correlate it because while the astronomers in the ancient Holy Land were not quite up to the task, there were 3 sets of astronomers who were up to the task and really were doing their jobs on a night-by-night basis. And these are the imperial astrologers of China, Japan, and Korea,
Okay.
who were looking at the sky every night as harbingers, either
Of anything,
for
good or bad. Yeah,
good or evil.
Yeah.
Because clearly the gods were up there,
Right.
and the emperor was a demigod.
Right.
So whatever was happening to the gods was affecting the emperor. So we'd better watch out really carefully and write down what was going on. And so from about 300 BC, but certainly from 0 BC onwards, there are pretty good nightly records in all 3 kingdoms. And the star of 1054, what's today, the Crab supernova is,
The Crab Nebula.
the Crab Nebula is detailed in great detail, wonderful detail in all 3 kingdoms' records.
Wow.
So we know all about it.
So we know that it took place
Took place.
on July 4th, AD 1054. And astrophysicists to this day celebrate with fireworks. I just want you to know. If you see us launching fireworks, that's what's going down.
That's so funny.
So you'd like to look for
So they would have had records for sure.
if there had been a really bright supernova,
Uh-huh.
or a really bright nova, 'cause
Bright anything, yeah, sure. sure.
a
Why
bright
not?
nova, a nova that's only, say, 100 light years away, and there are stars that are capable of becoming novas only 100 light years away, that is an easy star that can become brighter than Venus. So not quite a middle-of-the-day, scare-you-half-to-death brightness, but still pretty bright.
Still pretty bright.
So you got to go look really carefully at the Chinese, Japanese, and Korean records from, say, -10 to +10,
Yeah.
you know, AD, and there is no good candidate.
And there's no good
Yeah.
Okay.
Yeah.
Wow.
And by the
look
way,
at that.
planetariums
Yeah.
historically always had a Christmas show of the Star of Bethlehem. And was it a planetary alignment? Was it Venus? Was it this? Was
Right.
it that? But it really wasn't any of those, right? And
That's kind of a disappointing ending to a planetarium show.
but we got so sick of the show. I mean, it was just not. There was no science in it.
Yeah.
And so in the parlance of planetarium, you know what we call it?
The War on Christmas?
No. No, it was tradition. People come to see that, and they go to the Rockettes,
Right.
And that would be the
was a
holiday
kind of-
thing.
that makes sense.
No, but it became the SOB show,
SOB standing for?
Star Bethlehem.
There you go.
So we now have the technology. Astronomers now have the technology to once and for all answer the question.
Okay.
And I'm going to tell you how you heard it here first.
All right.
Using the kind of telescope I described, the one that found the
But what question are
supershell.
we answering now?
Was there a star?
Star of Bethlehem.
Was there a transient? Was there a bright nova or supernova
Right.
within, say, 10 years
Uh-huh.
of 0 AD?
Yes.
And we can actually answer that question now quite definitively. And within 5 to 10 years, certainly within 10 years, we're going to be able to give you that answer quite definitively.
Because you could,
Because you are looking right now.
because you're going to, because if it was something that exploded, you'd be able to see the remnant that's 2,000 years old.
And we're going to be able to track the expansion
Yes.
and then track the expansion backwards
Right.
to see when it
So
went
you will
off.
know.
You will know for a fact.
Oh my gosh.
And see, this is the cool thing about astrophysics because it comes with receipts. You know what I mean? You cannot bullshit. This is Cicero Artefan. What a cool name, Cicero.
We've had Cicero before.
Yeah, we've had
haven't
him
we?
before.
Unless there's more than one Cicero out there, but I doubt it.
There ain't no
There
two
shouldn't be.
Cicero Artefans. That's for sure. Hi, Dr. Tyson, Dr. Shara, Lord Nice. Cicero Artefan here from the cold lands of Toronto, Canada. We use these incredibly bright supernovae as standard candles to figure out how far away galaxies are. But it feels a bit counterintuitive, doesn't it? How can something so incredibly distant and that happened so long ago act as a reliable measuring tape for the cosmos? What's the ingenious method that allows us to use these far-off stellar explosions to gauge such immense distances?
That's a terrific question. These are the so-called Type 1A supernovae.
You weren't
And
happy
the-
with just two types of supernova, were you?
We had to subtype and subtype. The Type 1As are the magical supernovae that give us astronomers a yardstick. We want to know how far away something is so that we don't just see how bright it is, but how energetic it is. We can turn brightness into energy, into physical units.
Right.
And the Type 1As are something that we call standard candles, or equivalently, standard 100-watt light bulbs. They're
Candles
not,
were quite honored that we used them in this reference. I
Yes,
want you to
they
know.
did, and they,
It's very classical.
Yeah, since they really suck as a light source, they should be honored, but go ahead.
well, the standard candle was made out of whale blubber and
whale blubber
a
actually.
certain size.
Well, the oil lamps. Yeah,
oil
yeah.
lamps. I take it back then, because believe it or not, those actually burn pretty evenly. And
Well, if you have a big enough wick. Yeah, but go on.
That was the point. The beautiful thing about Type 1A supernovas is not that they are really all exactly the same intrinsic luminosity, but because we're able to measure the distances to some galaxies with other tools that we believe in very firmly, especially the Cepheid variable stars, and now the so-called tip of the red giant branch stars, we have a few hundred galaxies whose distances we know with great accuracy.
Nearby.
Out to perhaps 50 million light years.
Yeah, that's nearby.
okay.
50 million.
Our backyard.
Let's go there tomorrow.
And we see Type 1A supernovas going off there, and we can measure their light curves, their brightness as a function of time very precisely. And then we put them on the same graph, and we see that the brighter ones also last longer. But when we collapse them down to the same width, in other words, if we just shrink them digitally, both in brightness and in width, they all lie right on top of each other. So they are standardizable candles. Standardizable 100-watt light
like
bulbs.
That's great.
So the thing we can measure easily is how long they take to fade.
Yeah.
And then we use that how long they take to fade information to crunch down the light curve onto the standard light curve. And then we can look at supernovas that are 10 or 20 times further away than the furthest Cepheid. And that's how we can step way outside our backyard.
So it relies on the nearby calibrations, basically, to trust what the extrapolation is going to be.
And then you get far enough out to say, good grief, we thought the Hubble constant meant that the universe was always expanding at the same rate. Everything is cool. It ain't so. We have a change. We have an acceleration in the expansion of the universe. Where did that come from? Who ordered it? The so-called dark energy. We have no idea what it is, why it's there, et cetera, but it seems to be there, and that's because of the Type 1a supernovas.
Right, because because of your standardizable candle system, that it works all the way out to here. It's just that when you got to that point, beyond that, that's when things change. Well, something had to change because everything else coming from this point forward to us still works.
Everything still works. The physics is
Physics
fine.
works.
But it allows us to implicate the univerce and not the standard candle.
Standard candle.
Correct.
That's the point.
Correct.
Yeah, that's amazing.
And to answer the second part of the question, how did the universe figure out to do something like this? It turns out to be these wonderful white dwarfs. These collapsed objects actually have a maximum possible mass.
Right.
They can't get more than about 1.4 times the mass of the sun. If they do, then the gravitational forces within cannot be resisted by any pressure force without. And so there is a magic number.
They actually calibrate themselves for you.
There you go.
That's amazing.
There you go.
Oh my God, science is so crazy. I love it.
No, think about it. Because if the white dwarf would blow up at different masses,
right?
You don't know what you're looking at. But everybody's blowing up at the same mass.
It's just a little more complicated than that. But here's the one caveat.
I was proud for a second.
Because you can have two white dwarfs, a binary white dwarf, merge. And then you can be anywhere between 1.4 and 2.8 times the mass.
Gotcha.
So that would still count as a 1A supernova?
That'll still count as a 1A. And that's why you have brighter ones and fainter ones, and shorter decay times and longer decay times, because you have the little guys at the 1.4 and the bright guys at 2.8. Okay. And we've learned how to calibrate for that. Little extra complication.
So that's happened since I've been in graduate school. I don't think we knew that back in my day.
Nope.
Right.
Nope.
Now, so my little contribution to this,
Go ahead.
I am last author on a paper.
Last but not least.
Last author on a paper. The first author was Brian Schmidt.
Okay.
Nobel Prize winner.
Nobel Prize winner for co-discovering the dark energy with supernova type 1A. I'm on one of his supernova papers where, very proud of this, it is a supernova whose light curve does not fit the light curve of other supernova that it's supposed to until you invoke the expanding universe time dilation on its light curve.
There you go.
Then when you mathematically remove the time dilation of the light curve, it falls right back on cue.
Super cool.
So you get its distance and its speed with which is receding, and that rate stretches out the light curve. And so it was the first paper to demonstrate that. And now it's a routine correction that you make. So
let me just see if I got this right. The stretching of space is really what makes the difference.
Yes, and the stretching of space also stretches the time the time frame. That's correct.
Wow, you smart, man.
Well, no, there's 15 other authors on it.
Okay.
But they were all brave because the first time you publish something wildly different from what anyone else has ever seen, there's always this little nagging voice in the back of your mind. Did I screw up somewhere?
Right. They're all gonna laugh at you.
Am I going to be a laughing
Is this the
stock?
result? Is this interesting result of me screwing up? Right. Because if it matched other results, you all couldn't have screwed up in the same way. Right. So just to be clear about the timing. So if you are receding, and you're sending 1 pulse per second, let's say, but you're receding, the next pulse will not get to you after a second. It's a little longer.
Exactly.
Because you're now farther than when you sent the first pulse. And so that in a timed light curve will stretch out the light curve. That's all. And so this got corrected for, and there it was.
You say it like it's nothing, but that's pretty elegant if you think about it.
And he went on and got a bunch of these and got the Nobel Prize, and that was it.
Deservedly so.
I didn't get an invitation to the Nobel Prize.
Oh, well, listen, it's in the mail.
Michael, I think we have to quit it there.
Wow, that was great, man.
I mean, you're such a good talker. We didn't get to as many questions as we might have.
Sorry about that.
But they were good questions.
Yeah, they were great questions and great answers, and I learned a lot. So, well, this is I can actually tonight when I take my edible, I can think about all of this. I can think about all of this and really just like marinate.
Just before you do, though, I want you to check whether T Coronae has exploded.
Oh, I'll do
Just
that
before.
first.
Yeah, just look out your window.
Because
First, I'll check my neutrino detector.
there you go. Otherwise, you may see 3 or 4 T Coronae when you look out the window.
All right. Thanks, friend and colleague, Michael Shara.
Great pleasure. Thank you.
Chuck,
Always,
good to have you, man.
Always a pleasure.
All right. This has been yet another episode of StarTalk Cosmic Queries, the Exploding Stars edition. Oh, yeah. Neil deGrasse Tyson bidding you, as always, to keep looking up.